All right, so this video is for Lab 9 calorimetry, which is part of the thermochemistry chapter that you're going to be covering. So a couple of things that we want to just make sure that we are very, very clear on is when we talk about reaction enthalpy. So that's going to be the first important bit of terminology here. So reaction enthalpy is basically the study of energy changes that occur during a chemical reaction. That's what it is. All right, it's an important part of chemistry that involves studying energy changes that occur during chemical reactions. It's really just a fancy way of saying heat. That's what enthalpy is. Okay, it's a fancy way of saying heat. Because what we're talking about here is the way energy is exchanged between a chemical system and the environment by its evolution or absorption of heat, which we represent by the letter Q. So enthalpy is just a really fancy way of saying change in heat, okay? So the change in heat energy accompanying a chemical reaction is known as enthalpy, and we always look at that in terms of change in enthalpy. That's what that little triangle means. That's a delta. That means change. Change is always final minus initial. So by conventions, reactions in which heat is absorbed are labeled as endothermic and have positive values of delta H. So the way to remember that is if you look at just the terminology, right? Endothermic. Thermic because we're talking about heat, right? We're talking about energy. Endo means we are adding heat in. So endo, we are adding heat in, which means that our delta H values are always going to be positive here. And if a reaction is endothermic, then that means to us, because we are not a part of the reaction, if it's endothermic, that means it's absorbing energy from the surroundings. So remember, whenever we talk about something, we're always concerned about the system and then the surroundings. That's everything that's around the system. And for our purposes, because this is chemistry, the system is going to be the actual reaction. So if the reaction has a delta H that's positive, that means the system is absorbing energy. That energy is going into the system from the surroundings, which is why it feels cold to us. Okay, the surroundings begin to feel cold because the system is absorbing the energy. The opposite of that would then be an exothermic reaction. So for an exothermic reaction, now we're talking about heat exiting, okay, exiting the system. So here, heat is leaving, right? It's leaving the system, and the delta H here is negative in value. So if we look at our sort of pictograph up here, we have our system. Remember, that is our reaction. And here for this reaction now, it's giving off heat, right? It's giving energy out of the system, and that energy is going to the surroundings. So because that heat is leaving the system and going to the surroundings, it feels hot when we touch it, okay? So heat is released, that is an exothermic reaction. We label that exothermic, and it has negative values of delta H. So the most common examples of endothermic and exothermic reactions are cold packs and hot packs. You know, if you take a cold pack and you burst a little bubble inside, the whole thing gets cold, and it gets cold because once you burst that bubble, you release the water that then dissolves a solid, commonly ammonium nitrate. That's what we see here. So that water dissolves the ammonium nitrate, and that dissolution, that separation of that cation and anion requires energy. It requires energy. So that reaction, the dissolution, is the system, and it's pulling energy or heat from the surroundings, which is why the surroundings then feel cold. And we know this is endothermic because it has a positive change in enthalpy. So when we talk about the dissolution of a salt like this, an ionic compound, we don't write it here, but it's understood that this is happening in water, and ammonium nitrate is soluble in water. So what we really get here on the product side is the ammonium cation, which is aqueous, because it's soluble in water, and the nitrate anion, which is also aqueous because it's soluble in water. And this whole process requires 25.7 kilojoules of energy. So what we're saying here is that energy is going from the surroundings into the system, this whole thing being the system, which is why the cold pack feels cold. Hot packs would, of course, be the opposite, right? Once we expose the chemicals of a hot pad to air, it undergoes a reaction. That reaction is exothermic and it's producing heat. And that's why it feels hot. Another really important exothermic reaction is basically how you cook your food if you have a gas stove, or how you heat your house. So in this example shown here in equation 1, we can see we have methane gas combusting with oxygen gas. Remember, combustions like these always produce carbon dioxide gas and water. And here our change in enthalpy is negative. So we have a negative 890.4 kilojoules. So that heat that's being given off, right, this heat that's being given off, that's exiting the system. Remember, this combustion reaction here is the system. The heat given off is going into the surroundings, which, you know, is your house, or it's going into your food, right, if you are cooking your food using natural gas. So this is the most common example of a exothermic reaction. So we typically don't measure enthalpy directly. We measure it indirectly. What we like to do is use what's called calorimetry, where we basically run a reaction in some closed system that's insulated, and oftentimes in water. If we're doing calorimetry, typically it's in water. And so we run this reaction, and if the reaction produces energy, right, if it's exothermic, then this reaction basically is going to heat up the water that it's in. And so we can determine the heat transfer, the Q, if we know a couple of important variables. So Q is going to be the mass of whatever it is we're investigating, times what's called the specific heat. The specific heat is the joules per gram degree Celsius. So that's the amount of energy it takes to raise the temperature of 1 gram of substance 1 degree Celsius, times the change in temperature, where the change in temperature is the final temperature minus the initial temperature. So if we know Q here for one of these things, it allows us to do some really interesting calculations. So because we know the specific heat of water, and we know that energy can either be created or destroyed, we know that the total Q, or the total heat exchange of a system, is always going to be 0. So basically the Q of the reaction plus the Q of the water, if we're running in water, combined should be 0. So if we just rearrange this here, we know that the Q of the reaction is equal to negative Q of the water. So they're going to be equal in magnitude, but opposite in sign, because one is losing energy and the other one is gaining energy, right? So if the reaction is exothermic, then it is going to lose energy to the water, and therefore the water is going to get hotter, okay? So this is how we can basically determine the Q of a reaction, and then from there determine the change in enthalpy. And that's what we're basically going to do today. We're going to be looking at these transfers of heat energy, because we always have to go from hot to cold, right? Heat always travels from hot to cold, from a hot substance to a cold substance. That's really important. So if we took a piece of metal and we heated it up, and we then put that piece of metal in some water, we would expect, right, the water temperature to increase, because all of that heat energy from the metal is going into the water. So the water temperature will increase and the metal temperature will decrease until they reach thermal equilibrium, where the temperatures are now the same. So we can do the calculation of that transfer of heat energy from the metal to the water by using this basic equation of Q. So if you scroll down here in your lab, you can see equation 7, where it shows you that the Q of the hot object here is equal to the Q of the cold object. Again, same magnitude of number, but opposite in sign, because a hot object is losing energy to the cold object. And one of the best ways to do these calculations is to use what's called a calorimeter. And a calorimeter is just an insulated reaction vessel where we can run the reaction inside and then determine the change in temperature by just reading, a thermometer probe. Now, calorimeters are not perfectly insulated. That's really important. We like them to be, but they're not. So that means that we can't just write this simple, sort of Q the hot equals Q the cold, right? We have to look at equation 4 here. So if we took something that's hot, like in this case in our lab, we're going to be using pennies. So we're looking at the Q of copper, because pennies are made of copper. So we have the Q of the copper is going to be equal to the Q of the water, right? Because all the copper is going to absorb into the water, plus the Q of the calorimeter, because the calorimeter is going to absorb some energy. And we're using absolute values here, okay? The signage of the negatives and positives, it just denote directionality, okay? Just denotes directionality. So what we're going to do in this lab is, first we're going to measure the change in heat, or the Q, for the dissolution of some salts. So we're going to just dissolve some sodium chloride in water, some calcium chloride, and some potassium chloride. And we're going to just determine the Q of the dissolution of the salt. What is that heat transfer? And then the joules per gram of that salt. That's part A. And then in part B, what we're going to do is we're going to calculate the Q of the calorimeter, because we want to know how much heat is actually going to be absorbed by the calorimeter. And then once we know that information, then when we move on to part B, we can use that if we want to determine the specific heat of copper. And so we're going to do the specific heat of copper 2 ways. We're going to assume that all of the heat was simply transferred to the water and none was lost to the calorimeter. And then we're also going to do the calculation understanding that some of the heat from the copper is going to be lost to the calorimeter. And again, Q here of the copper is simply the mass of the copper times the specific heat of the copper times the change in temperature. The Q of the water is going to be the mass of the water times the specific heat of water times the change in temperature of the water. And then the Q of the calorimeter is a little bit differently. Instead of using specific heat, where the units here are joules per gram degree Celsius, we're going to use instead the heat capacity. So the Q of the calorimeter is simply equal to the mass times the heat capacity of the calorimeter. So that's, actually, let me call that C for heat capacity of the calorimeter. And this is simply going to be joules per gram. So let's take a look at the calculations for part A. So again, for part A, we're just looking at the Q for the dissolution of these various salts. Again, when we say dissolution of a salt, what we mean is we're taking a salt, like sodium chloride here, which is a solid, we're putting it in water, and we're separating the cation from the anion, okay? So the equation looks like that. We're just separating the cation from the anion. So the question is, does this process require energy or does it release energy? Is it endothermic or is it exothermic? So you can see here, I just have some data that was previously collected. We have the mass of the test tube, the mass of the test tube in water. The difference between these will then give me the mass of the water. We have the initial temperature of the water, the mass of the test tube, the mass of the test tube and the salt. The difference between these two, of course, gives me the mass of the salt. And then we have the final temperature Again, that's going to be the peak temperature that it reaches. And the question is this endothermic or exothermic? So if it produces enough heat, you could tell it's exothermic, right? It's going to get very hot. Or if it absorbs enough heat, you can tell that it's endothermic because it's going to get really, really cold. Sometimes it's not quite so clear cut, and the sodium chloride is one of those examples where it's not quite as obvious, especially if you're stirring it a little too quickly. So the key here is you're going to want to do these calculations. So let's calculate Q for the dissolution of the salt. Now we don't know the heat capacity of salt, right? Remember, our Q formula is Q is equal to the mass times the specific heat times a change in temperature. We don't know this for the salt, but we do know it for water. So we do know that Q of the water is going to be equal to the mass of the water times the specific heat of the water times the change in temperature of the water. And we also know that all of the energy associated with this dissolution of the salt should be equal to the energy absorbed by the water, just opposite in sign. Okay? So now that we know that formula here, we can go ahead and do the calculation for the dissolution of this sodium chloride. So basically what we're finding is the Q of the water. And then from there, we're going to calculate the Q of the salt because we just have to change the sign. So we need to use the mass of the water, which in this case was 1.64 grams. The specific heat of water is 4.184 joules per gram degrees Celsius. That's given in the table in the lab. And then the change in temperature is always going to be the final, which in this case was 22.5, minus the initial temperature, which was 24.0 degrees Celsius. So you plug that into your calculator and you should get 10.3, right? This is going to be negative 10.3 joules. If we look at our units here, right? Grams cancels, degrees Celsius cancel, and we are left with joules. And since the Q, let me erase that. Since the Q of the water is equal to the negative Q of the salt, right? Just changing the signs here. Then what we have here is negative times negative 10.3, and that tells us that we have 10.3 joules. Make sure you write your units. So this is a positive value, so this is an endothermic process. So in order to dissolve the sodium chloride into its sodium and chloride anions, this required an input of energy. So that's how you do the calculations for part A. Okay, so let's look at this bit of data right here with the change in temperature. Okay, so we can see here from the change in temperature that the water got colder, right? The temperature decreased. And the reason why the temperature decreased is because any thermal energy or heat that was in the water got absorbed or taken in by the salt in order for the dissolution to happen, okay? In order for the cation to separate from the anion. So the water decreased in temperature, therefore it got colder, right? Because the Q was being absorbed by the salt dissolution, and therefore that's one way we know also that the salt dissolution was endothermic. Also because we have a positive Q here, 10.3 joules. So that's how you do part A. For part B, what we're doing is we're trying to determine the heat capacity of the calorimeter. Remember, ideally we want all the heat to transfer from, say our salt to our water, or from our hot metal into our water, but some of it is going to be absorbed by the calorimeter, and so what we have to determine is how much of it is absorbed by the calorimeter. So that's what we're doing in part B. We're going to determine the Q, the heat gained by the calorimeter, and then use that information to calculate the heat capacity of the calorimeter in joules per gram. All right, so let's look at this data here. We had the mass of the calorimeter. Those are our coffee cups and the lid. We had the mass of the room temperature water. Again, this should be to 2 decimal places. That's really important because the scales that you use read to 2 decimal places. So 2 decimal places here, 2 decimal places here. We have the temperature of the room temperature water. That should have at least 1 decimal place. That's really important. The mass of the hot water, the initial temperature of the hot water, and the final temperature of the system. The system being the entire thing. The calorimeter and the water, all of it comes to this final temperature. So let's look first at the Q lost by the hot water. Okay. So what we're doing is we're adding hot water into basically room temperature water, and then we're going to note how much energy goes from the hot water to the cold water. Now remember, the hot water Q should equal the cold water or room temperature Q, assuming there's a perfect heat transfer, right? They're just going to be opposite in sign. But we know that's not going to be the case. We are going to lose some heat to the calorimeter. So this is what we're trying to figure out. The Q of the calorimeter and the heat capacity of the calorimeter. And if you look at your lab manual equation 4, right, it tells you to use the absolute values here. Okay, so let's go ahead and work through this calculation. The Q lost, oops, sorry, that does not look like what I want it to look like. So the Q of the hot is going to be equal to the mass of the hot water. So the mass of the hot water is 49.63 grams. The specific heat of water is 4.184 joules per gram degree Celsius. And then the change in temperature is going to be the final temperature of the system minus the initial temperature of the hot water. So the key here is to make sure you're using the values associated with the hot water for the Q of the hot. All right, so 53.7 minus 86.9 times 4.184 times 49.63 tells us that our Q of the hot is negative 6894. This is 4 sig figs, 4 sig figs. The change in temperature, 53.7 minus 86.9. This change in temperature, if you actually write it out, is 33.2, negative 33.2 degrees Celsius. So that means we should have 3 sig figs here, right? So this would be negative 6890 joules. Okay. Again, make sure you write your units so that you can see your units cancel. All right, we have to do the same thing for the cold. Set it up the same way. So now we're going to use the mass of the cold water, which was, or the room temperature water, which was 45.74 grams, right? This value right here, times the specific heat. They have the same specific heat because it's all water, times the change in temperature. 53.7 minus the initial temperature of the room was 18.9 degrees Celsius. So 53.7 minus 18.9. I'll just jot this down in terms of sig figs, right? This is 34.8 degrees Celsius. So times 4.184 times 45.74 gives us a Q of the cold that is 6659.89 joules. This should be 3 sig figs. So that means we want to keep these 3 here. So that gives us 6660 joules for 3 sig figs. So now that we have these 2 values, we can go ahead and plug them in up here to find the Q of the calorimeter. And it says to use the absolute value, so that's what we're going to go ahead and use. We have 6,890 joules is equal to this 6,660 joules plus the Q of the calorimeter. So you just have to do subtraction here. So 6,890 minus 6,660 tells us that the Q of the calorimeter is equal to 230 joules. And so that's what you would write here. Q the calorimeter, 230. So we know this value was 6660 and this one was 6890. Okay? So the last thing we have to calculate here is the heat capacity of the calorimeter. So we know that the heat capacity, or excuse me, the Q the calorimeter is equal to the mass of the calorimeter times the heat capacity. So here we have 230 joules is equal to the mass, 187.32 grams, divided by what the heat capacity is. So you have to do that division to solve. And so here we have 1.227 joules per gram would be our heat capacity for the calorimeter. Okay, 2 sig figs, so we would, because this is 2 sig figs, so we would say 1.2 joules per gram for our heat capacity of our calorimeter. 1.2 joules per gram. Now, it doesn't tell you here, but you will need the average Q gained by the calorimeter in part C. So that's what we're going to do next. We'll do the calculations for part C. So in part C, now what we're doing is we're going to find the specific heat of copper. And we're going to do it assuming that no heat is lost to the calorimeter. And then we're going to calculate it using the calorimeter Q absorbed from part B. So when they say that, they mean this right here. We're going to need the average here of the Q gained by the calorimeter. All right. So let's go ahead and look at this calculation. So for this calculation, you know, we have our copper pennies, and we know that the heat from those hot pennies should go into the water. And we understand that we're going to lose some to the calorimeter, okay? But initially, we're just going to focus on this part. Initially here, where it says specific heat of copper, assuming no heat loss to the calorimeter, that means we're going to assume for this calculation that the Q of the calorimeter is 0, okay? So again, the Q formula for the copper pennies and for the water is the same thing. It's just mass times specific heat times the change in temperature. So we have here the mass of our pennies, which was 31.31. Let me change the color. 31.31 grams. And we do not know the specific heat of the copper. That's what we're looking for. And then we have the change in temperature. So the final temperature was 29.8, and the initial temperature is the initial temperature of the pennies, which is 93.9 degrees Celsius. So we can go ahead and sort of do part of this. Actually, you know what? Let's start with the Q of the water. I think that might make a little bit more sense since we have all of that data. Let's start with the Q of the water instead. So the Q of the water is equal to the mass of the water, which is 23.54 grams, times the 4.184 joules per gram degree Celsius, times the change in temperature. So the final temperature of the system was 29.8, and we started at an initial temperature of 23.9 degrees Celsius. That makes sense because we would expect the water to gain, absorb the energy from the copper, and so we would expect it to increase in temperature. So 29.8 minus 23.9. This is actually 5.9 degrees Celsius. We're going to need to know that for our sig figs. So 5.9 times 4.184 times 23.54 tells us that the Q of the water is 581 joules. So we are going to write that as 580 joules so that we have 2 sig figs. And because we're going to assume the Q of the calorimeter is 0, then that tells us that the heat that we gained, right, this 580 joules from the water has to equal the heat that was lost by the copper pennies, okay? So now we can go ahead and say, all right, well, I know the mass of my pennies. I'm looking for S, and then I have a change in temperature. So the final temperature was 29.8, and we started at 93.9 degrees Celsius. That makes sense because we would expect, right, the copper to have lost energy. So 29.8 minus 93.9. This value here is negative 64.1. So then we just have to solve for S. So 580 divided by the product of 31.31 times 64.1. So S here is going to be 0.2889, excuse me, 9, and it's going to be joules per gram degree Celsius. We can ignore the sign here because specific heats are always a positive value. All right, so that tells us that we had 580 here, and the specific heat of our copper is, we should have, let's see, 3 sig figs, so 0.289 joules per gram degree Celsius. Okay? And you're going to do that, of course, for trial 2. Now, for this next calculation down here, the specific heat of copper, assuming that the Q of the calorimeter is no longer 0. So remember, in this first way we did this specific heat, we assumed that the Q of the calorimeter was 0, but now we aren't. Now we're going to actually apply, actually I'll just leave this up. We're going to actually apply our values from part B to this. So my Q of the calorimeter, the average was 190. So now here what we have is this. Now I'm going to say, well, the Q of the copper is equal to the Q of the water, which I just determined was 580 joules. And I know that the calorimeter absorbed on average 190 joules. So here I have 580 plus 190. That gives me 770 joules. And that should be equal to the Q of the copper, okay, of the pennies. Q of the copper. So this value is going to be equal to the mass of the pennies, right, times the specific heat, times the specific heat, times the change in temperature, which was 29.8 minus 93.9 degrees Celsius. So then you have to solve for S here. So 29.8 minus 93.9. This was, right, negative 64.1. Excuse me, that's a 4. Negative 64.1. So 770 divided by the product of 31.31 times 64.1 gives us a specific heat of 0.3836 joules per gram degree Celsius. And we should have, well, this is just 2 sig figs, so we're going to keep this at 2 sig figs, so 0.38 joules per gram degree Celsius. So 0.38 joules per gram degree Celsius. which we can see is really close, right? It tells us that the specific heat should be 0.386. So we're going to go ahead and do our percent error. Remember, percent error is what you got, the absolute value of what you got minus what you should have got, right? Divided by what you should have got times 100%. So 0.38 minus 0.386 divided by 0.386, absolute value. So then we say times 100. So this gives us a 1.5% error. Pretty good. We can see here that if we don't take into account the calorimeter, we have a very different value for the specific heat of copper, right? We would have a much greater percent error. So this just demonstrates really that you do need to take into account the heat that is absorbed by the calorimeter, because these systems are not perfectly insulated. They will absorb some of the energy. All right, I hope that sort of clarifies how you do these calculations. When you're looking at the pre-lab, let's just scroll up here to the pre-lab questions. Really quickly, let's talk about number 3. So here it tells you if the mass of the calorimeter, what's the heat capacity of the calorimeter. So this is actually part B, right? This is just like part B calculations. Number 4 is like part C, right? Because here it tells us all this information. It wants the specific heat capacity of the metal. And then part 1 just takes advantage of your understanding of basically, instead of molar ratios, now we're doing an energy molar ratio. So it tells you to refer to equation 1 up here, which is the combustion of methane that we talked about when we talked about heating our homes. Right here. And we can see from this reaction that we had, for every 1 mole, right, for every 1 mole of methane, we produced, there were negative 890.4 kilojoules. Or we can say for every 890.4 kilojoules of heat that was produced, we reacted 1 mole of methane. So instead of using your moles to mole ratio, now you're just going to use the sort of molar to energy ratio. So if you know the grams of methane, right, then you know the moles of methane, which means you can determine the change in enthalpy for this reaction. So that's what they mean by refer to equation 1. And then it's not explicitly stated, but question 2 is related, right? You can see here that you have the same amount of methane in each of these equations, right? Each of these questions, 4.05 grams from above. This is, 4.05 grams from above. So these questions are actually connected. You need this answer to solve for question 2. Okay? All right. Email me if you have any questions. It's a pretty straightforward lab in terms of collecting the data. You just have to make sure that you're, recording all of your temperatures correctly, your masses correctly, and then make sure you work through your calculations using the appropriate number of sig figs and units. I will be checking all of these calculations to make sure that they are correct. And then, of course, there will be post-lab questions that you have to answer.